In this unit, we continue our discussion of circuits with batteries and resistors. For circuit analysis, circuits can be represented by simplified diagrams. A resistor, in this case the light bulb, is represented by a zigzag line. A battery is indicated by a pair of parallel line segments of different lengths. The wires are indicated by the connecting lines. In this unit, we consider simple circuits that include batteries and resistors. A battery has a positive and a negative terminal. In the symbolic representation of a battery, the positive terminal is indicated by the longer of the two line segments. The negative terminal is represented by the shorter line segment. Chemical reactions in the battery maintain a higher voltage at the positive terminal than at the negative terminal. Devices that maintain such a potential difference produce an electromotive force, or an EMF. The EMF is represented by the symbol epsilon and is directed from the negative to the positive terminal. There are other sources of EMF besides batteries, for example, electric generators. In spite of its name, the electromotive force is not a force. The electromotive force is the increment of work, delta W, done on charge, delta Q, in moving from the negative to the positive terminal. The EMF drives a current I in the direction shown. The unit of EMF is volts. Consider a given point A in the simple circuit shown. If the electric potential is defined, the sum of potential changes around any closed loop must be zero. Let's make a round trip through the circuit in the direction of the current flow and add up the potential changes. As we move from point A to point B, the potential increases by the value of the EMF, epsilon. The potential at point B is therefore the potential at point A plus the EMF. The increase in electric potential across the battery is consistent with the increase of potential energy of the charges moving through the EMF. Proceed across the resistor back to point A. The resistor has a resistance R. The potential change across the resistor is negative IR. The electric potential across the resistor drops. This is consistent with the decrease in potential energy of the charges across the resistor. Because the net change in potential around the complete loop is zero, we can subtract the potential at point A from both sides of the equation. We are left with a relation between the current, the resistance, and the EMF. We can solve this equation for the current. The theorem that the net voltage change around a closed loop is zero is called Kirchhoff's second rule, or the Loop Theorem. It applies to more complex single-loop circuits as well as multi-loop circuits. To apply the Loop Theorem, increase the voltage by epsilon crossing an EMF from the negative to the positive terminal. Decrease the potential by IR when traveling in the direction of the current across a resistor. We need to add one detail about batteries and other forms of EMF. In addition to whatever resistance exists elsewhere in the circuit, all batteries possess an internal resistance that cannot be removed. Let's add an internal resistance, small r, and determine its effect. We draw a box around the EMF and the internal resistance to emphasize that they are both properties of the battery. Now, let's apply the Loop Theorem to the circuit beginning at point A. The potential increases by epsilon across the EMF, but decreases by I times the internal resistance, small r. Across the external resistance, capital R, the potential drops by IR. We know from the Loop Theorem that the net potential drop is zero. This can be solved for the current I. What is the voltage across the battery now? We must include the internal resistance. The voltage at point B minus the voltage at point A is VAB, and is given by the EMF minus I times the internal resistance. We can plug in an expression for I from the other equation as shown. This is the voltage that would actually be measured across the battery terminals and is called the terminal voltage. it is always less than the EMF. When the internal resistance is much smaller than R, the internal resistance has only a small effect on the voltage, and in such cases, it is often ignored. If the resistor R is 1 ohm, the current through the circuit shown is 4.55 amperes. If the resistor R is replaced by a 0.5 ohm resistor, the current increases to 8.33 amperes. What is the EMF of the battery? Try again. Try again. Correct. With the loop theorem, it is straightforward to solve for the current through any single loop circuit. Let's consider a circuit with 3 resistors R1, R2, and R3. Let's ignore the internal resistance this time. Apply the loop theorem. We will begin at point A. Proceed in the direction of the current flow. The potential increases by epsilon across the EMF. It decreases by IR1 across the first resistor, by IR2 across the second resistor, and by IR3 across the third resistor. Once again, the equation can be solved for the current I. When the same current flows through multiple circuit elements, we say that they are in series. The 3 resistors shown here are in series. When resistors are in series, as in this case, the voltages across each resistor are proportional to the current. Let's consider the general case of some number n of resistors. The voltage across each resistor is the current times the resistance of that resistor. The current can be factored out on the right-hand side. The combined effect of all the resistors is the same as one equivalent resistance R sub EQ, which is equal to the sum of the individual resistances. As we will see later in this unit, for more complex circuits, the effect of a network of resistors can be reduced to an equivalent resistance. For resistors in series, the equivalent resistance is equal to the sum of the individual resistances. A circuit has 2 resistors and a battery. The internal resistance of the battery is 0.2 ohms, and the resistors have resistances of 0.6 ohms and 0.4 ohms. The EMF is 5 volts. What is the terminal voltage? Correct. To make a point about using the loop theorem, let's return to a simple circuit that includes only an EMF and a resistor. In this simple circuit, the direction of current flow is obvious. Sometimes in more complex currents, it is not so obvious. Let's solve for the current in this circuit under the assumption that the current is flowing as shown, in the wrong direction. When we integrate around the circuit in the same way as before, the jump in voltage across the EMF remains the same. Because we are traveling against the assumed current direction, the voltage increases across the resistor. Next, we'll solve this for the current. The result is the same as before, except the sign is now negative. This indicates that the current flow is opposite the assumed direction. Applying the loop theorem gave the same result, even though the assumed current direction was wrong. In general, when we solve circuit problems, we can simply choose a direction for the current. A negative result indicates the current is actually flowing in the opposite direction. The circuit shown includes 2 batteries, each with an internal resistance and an additional resistor R1. Note that the 2 EMFs are in opposite directions. We will apply the loop theorem to the circuit shown, beginning by moving in the direction of I across the first battery in the direction of its EMF. The voltage will increase by epsilon 1 and decrease by I times small r1. The circuit path goes through the second battery. Because we are traveling in the direction opposite to the EMF of this battery, the voltage decreases by epsilon 2 and by I times small r2. Finally, we complete the circuit by crossing resistor R and returning to the starting point. Solve this equation for the current. If epsilon 1 is greater than epsilon 2, the current in the second battery will flow against its EMF. This indicates that energy is being added to this battery. That is, it is being recharged. Using this type of arrangement won't recharge most real batteries, however. In fact, the battery may explode. In this circuit, epsilon 1 is 5 volts, epsilon 2 is 2 volts, small r1 and small r2 are both 0.4 ohms, and capital R is 2 ohms. What current is flowing through the circuit? Try again. Correct. In the circuit shown, a current of 2.5 amperes is flowing through the circuit. What is the voltage across the 2 ohm resistor? Correct. What is the net power being generated by the first battery with an EMF epsilon 1? The current is 2.5 amperes. Correct. In this circuit, we have a battery with an internal resistance. For what value of resistance, R1, is the power dissipation in this resistor the greatest? The power dissipated in the resistor R1 is the current squared times R1. The internal and external resistances are in series, and we can write down an expression for the current. Substitute this representation into the expression for the power. Let's plot the power as a function of R1. The axes have been put in terms of epsilon and R. The important thing to note is that at first the power increases as R1 increases, but then it decreases. Let's calculate the maximum value of the power. How do we find the location of the maximum value of this function? Correct. To find the maximum, take the derivative of the power as a function of R1. The result is as shown. This condition is satisfied when R1 is equal to the internal resistance small r. Using this result in the equation for the power shows that the maximum power is 1/4 epsilon squared divided by the internal resistance. Consider the arrangement of resistors shown. The current entering from the left can travel through either of the two resistors. According to the Loop Theorem, the sum of the voltages around the loop formed by the two resistors must be 0. Therefore, the voltage drops across V1 and V2 must be equal. When the same voltage drop takes place in 2 or more resistors, they are said to be in parallel. This voltage drop is equal to the voltage drop across the circuit. Let's consider the currents I1 and I2 through each resistor. If the current is not to pile up anywhere, the sum of I1 and I2 must be equal to I. Now we can determine the equivalent resistance Req of the two resistors in parallel. Substitute the expression for I into this equation. The current across each resistor is the voltage divided by the resistance. Because V1 and V2 are both equal to V, we can make the substitution as shown. The voltage can be factored out. Divide both sides of the equivalent resistance to get this final expression. In a steady-state circuit, current cannot accumulate anywhere. Therefore, the current flowing into a junction must equal the current flowing out of the junction. In this case, the current I1 flowing into the junction is equal to the sum of the other two currents flowing out. In applying the junction rule, it is important to keep track of which current is flowing into the junction and which is flowing out. If we adopt the convention that current flowing into the junction is positive and current flowing out is negative, we can make the following statement. The algebraic sum of the currents at a junction is zero. This rule is known as the Junction Theorem, or Kirchhoff's first rule. What is the value of current I at the junction shown? Try again. Correct. Once we know the equivalent resistance, we can solve for the currents in this circuit. Let's work through an example. Suppose current I is 2 amps, R1 is 2 ohms, and R2 is 4 ohms. What is the total current, and what are the currents through each resistor? The equivalent resistance is calculated as shown. Here is the equivalent resistance. The voltage across the resistors is the current times the equivalent resistance. The current through each resistor is determined as shown. Now we consider the general case of resistors in parallel. We will determine the equivalent resistance for n resistors in parallel. The total current is divided among the individual resistors. The voltage across each of these resistors is the same. The current through each one is that voltage divided by the resistance. Divide both sides of this equation by the voltage times the equivalent resistance. This gives us the general solution that, for resistors in series, the inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistances. Which of the following statements is true? Correct. If each of the 4 resistors has a resistance of 4 ohms, what is the equivalent resistance? Correct. How would you connect a second resistor to this circuit to decrease its resistance? Correct. What is the equivalent resistance of this circuit? Correct. What about a more complex network of resistors like the example here? We can often simplify a relatively complex circuit by grouping resistors together. Start by noting that resistors R3, R4, and R5 are in parallel. The equivalent resistance, Rp, of these 3 resistors is given by the equation shown. In effect, we have reduced these 3 resistors to 1. These 3 elements are in series. We can now write down an expression for the equivalent resistance for the entire set of resistors. In the circuit shown, the terminal voltage of the battery is 10 volts. What is the voltage drop across the 1 ohm resistor? Try again. Correct. In general, it is not always possible to solve a circuit by reducing it to equivalent resistances. When this is the case, the loop and junction theorems must be applied to create a set of equations to find the currents and voltages. For example, consider the circuit shown. First, we define currents I1, I2, and I3 that pass through the corresponding resistors. The direction of these currents can be chosen arbitrarily. If the current is actually flowing in the direction opposite to the direction chosen, it will be negative in the solution. Let's consider the junction marked X. All 3 currents are directed into the junction. From the junction rule, we know their sum is 0. The equation for this is shown. Next, apply the loop rule to the right-hand loop of the circuit as shown. This gives a second equation as shown. Apply the loop rule to the left-hand loop to find a third equation. Now we have 3 equations and 3 unknowns, which we can solve for the currents. Click on the Show Derivation button to see how to do this. In this circuit, figure the EMF, epsilon, is 9 volts, R1 is 2 ohms, and R2 is 6 ohms. What is the magnitude of the current that passes through the wire that is marked A? Try again. Correct. Now we will consider devices used to measure current and voltage. To do so, we will use the simple circuit shown as an example. An ammeter is a device that measures electric current. To measure the current in the circuit must be broken to insert the ammeter, as indicated in the example circuit. The ammeter is shown as a circle labeled A. It is necessary that the ammeter change the current through the circuit as little as possible. Therefore, the ammeter must have a resistance that is much less than the other resistances in the circuit. To measure the voltage between 2 points in a circuit, a voltmeter is used. In our example, the voltmeter measures the voltage across resistor R. It is indicated by a V enclosed by a circle. It is connected in parallel to the resistor. The internal resistance of the voltmeter must be high to obtain an accurate measurement.